first step is where the sample is received. You have to find a way of extracting or separating the virus, if the person has it, from the liquid with which it is brought from the field or from where it was picked. The second part is that when we are looking for the virus, we don't look for the whole virus. We look for parts of the virus, particularly the genetic material, because every organism has a specific genetic material, and that's the way you're able to distinguish different organisms. So for coronavirus, we have a way of looking at the genetic material. So the kind of test we do for COVID-19 is not your typical sort of dipstick test where you're able to just take a sample, drop it on a dipstick or on a stick, and then you get a development of a color. So it's not like, for example, test for malaria, which you do a rapid diagnostic test, or even, let's say, a pregnancy test where you have a strip which you dip into urine, and after a while it shows the color showing that the person is pregnant. With COVID-19, there is a lot of expertise required. There's expertise required in picking the sample from the nose or from behind the back of the throat. If you don't take the sample properly, then you're not going to get a good result. There is expertise required in extracting the genetic materials, I've said, and not just expertise, you also require the right equipment. There is expertise required in reading the results. Again, the results are not as simple as a negative or positive, and so you require the right equipment, you also require the right expertise. The other part that is really critical is quality control, and again, you have met some of our quality control officers, and quality controls begins from labeling of the sample to ensure that you have the right name tied to the right sample. There's quality control of how you're doing the testing itself, their standard operating procedures. There's quality control of how the results are recorded and stored, and then even transmitted forward to the national team for announcement.
Why are we seeing
I think, obviously, there are a combination of things. One, it's possible that we are getting more increased community transmission over time. The way a virus transmits is, for example, if one person gets it, they could infect another 5 people. If the 5 people get it, then they could infect another 25, and that you get what we call exponential increase. In other words, it's like multiplication. And so it's possible that what is happening now, we started with a small number, but those numbers have been infecting other people, and now we are starting to see that multiplication effect. The second part is also potentially because we have increased our testing capacity. And so we are testing more people, and obviously when you start testing more people, you're more likely to pick up some of the people who you may not have picked up had you not tested. So it's a process that takes almost 12 hours. And at each step, one has to be extremely careful that they are following the standard procedure to ensure that the material that you move from one step to the next, to the point where you test, and to the point where you read out, you're keeping the quality. And in fact, the people you have seen doing this test here at the Chem Welcome to Research program are people who have had years of experience in research, and specifically around viral research and genetic research. So on average, people like Charles Nyegoti, who you saw today testing, has been here for the last 12 years and did his PhD on viral research and continued after PhD to work on viral research. And so he's got a very good understanding of the processes and has the expertise to ensure that you're getting high quality and reliable results. When we receive the samples, first of all, the samples come in what you call a transport media. So it's a liquid which allows the virus to continue living and not completely disintegrate in a way that you cannot then pick it up in a test. And that is supposed to be transported cold, so in ice packs. And when they get here and we extract these various, as we get the materials that we are then going to test, those materials are stored at very low temperatures. We have the big freezers that you can see behind us. These are like your home freezers, except that the home freezer is at minus 20 degrees, and these are at minus 89 degrees, which means that they ensure the integrity of the materials that we are working with, or the materials that we are testing.
So all this research is led by PIs, and they have a team of individuals from PhD students, master's students, and lab technicians and research officers. And the research is supported by the laboratory platform. We have 3 main labs: the clinical trials lab, the immunology lab, and the microbiology lab. In addition, we have teams to support the laboratory and research, to support the laboratory and support the research work. And those teams involve the field team, those that go out into the community and collect samples to allow us to understand the diseases we're investigating. We have a biobank team that manage all the samples in -80 storage, and the biobank samples are about 1 million. We have a data and IT team that supports the equipment and machinery that we have to support the research work. And we have a lab and health and safety team and a quality assurance team. There are sort of 4 broad areas that we cover. One would be the molecular, where we look at the genetic material of the agent or the microorganism that's causing the disease. And that means we look at either DNA or RNA. And the idea behind that is to see, can we quantify this DNA? Can we see how it's changing in infections? Or what sort of materials is it producing to cause the disease? And the second aspect is cellular. So we're trying to understand, how does the human who's infected with the disease respond to the infection? How does it fight off infection or defend itself against infection? What sort of cells or molecules is it producing to protect itself or to sort of heal itself from infection? Then we have 2 other categories, which are vaccine trials and drug trials. Within the vaccine trials, we take what we understand about the immune system to investigate or to support the vaccine trial work that we're doing. And the vaccine trial work covers understanding how safe is the how safe is the vaccine, and how is the human responding to what they've been given in the vaccine. And then you monitor these individuals and understand how long should you give that vaccine for. And then the final aspect is also around understanding the medicines that we use to cure these diseases. How long are they given for, and what's happening to the body as it's being given, and what's happening to the agent as you give that medicine. So all these areas cover all the diseases. And so what we've done as a department is use that expertise to now support the COVID-19 testing work that we're doing, and to understand the SARS-CoV-2 virus. With the current tests we're using, they're a bit limited with your numbers because of the process that I explained. COVID-19 testing is not just about the sample that's collected in the community. When it comes here, we have to extract the RNA, and then we have to go through a polymerase chain reaction to amplify that RNA and look if an individual has those copies. And that process for us can take up to 12 hours. So if you had an antigen test, which then you can take a blood sample from individuals and screen, you could tell pretty quickly how many individuals have seen SARS-CoV-2 infection. So that's what we are looking to do in terms of developing an antibody test to do a quick screen of the population rather than the current method that we are using.